Velocity and acceleration. Okay, basically before you get started, you might want to start reviewing how to graph functions, how to find the first derivative, how to find the second derivative, and understanding the rates of change, because these next problems I'm going to go through, they're applications and real life examples. And basically some things we need to establish is that the first graph will usually represent the displacement or the position of a certain object. So it's usually going to be written as ST, T representing the amount of time in which the motion was occurring, and ST is usually going to be the displacement, whether there was positive or negative movement. And then the instantaneous velocity is basically the slope of the tangent line, or the first derivative, and it's going to be usually written as VT, or as the derivative of ST. And the acceleration is going to be written as it should have been AT. And basically it's just the derivative of velocity and the derivative of the second derivative of position. And then the last one is just basically the same thing as velocity, but it's just the absolute value, because remember, speed and velocity, they're both the same thing, but velocity is just the measurement with direction. So yeah, this is just me going through the same thing of the first function. So for example, if you have a problem like ST equals 3 t cubed minus 6t squared plus 9t plus 1, the t is just basically saying, this graph is just basically a representation. So if I was to graph quickly the line right here, well, poorly drawn, but it would look something like this. And basically just the x-axis is the x-axis is going to be t, and then this over here is going to be st. So basically the line is just, I'll go more into detail right now. Go on the next one. Okay, so the first derivative usually represents as I said before, the slope of the tangent line and speed and velocity, because as you see here, this point is going to continue progressing through the line. But as you see the slope right here, since the line is going up, then therefore the slope is going to be positive, and therefore the velocity is going to be positive, because what's happening is that as it keeps moving from here to here, down and up, also known as the slope, as it's going to keep going and going, it's going to be an increase in, it's going to be positive velocity. So therefore, that's positive velocity. But as you see here, if they were to start showing the progression of how this line came to over here, you would see that the line itself is something down with a negative slope. But as it continues, at this point right here, it flattens out, and therefore there's no velocity at this point. But as it continues to progress, the velocity once again becomes positive, and it just starts shooting to positive infinity. Next. So here's just basically the same problem, the first derivative, and this is how you would more or less solve it. You would find the first derivative, and then factor it down, and then obviously you would set it to 0. You would set it to 0 to find where the slope of the tangent line, or the velocity. Because remember, if you have a curve, at that point right there, the line flattens out and it's 0. So we're trying to find points like these in which the velocity increases or decreases. So you will set it to 0. So basically t would equal 1 and t would equal 3. So basically, if you were to try, if you want to help, if it helps, I'll draw the wiggle graph, which is so basically, at 1 and 3, these are the critical points in which where it's 0 and 0. And then if you want to continue plugging in points, you'll see that like 2, for example, it would be 4, 3 minus 12t plus 9. What? Then it would be 12 minus 36 minus 9 I think we would get a negative answer. So right here, the line goes to 0, and then the velocity decreases. This is more or less how the line would look. See how right here at 1, the critical point, the slope evens out, but right here it begins to start decreasing once more. Okay, so this is the second derivative, which basically represents how fast or slower the velocity is increasing over time. So if I was to start showing this line when it started over here, you would see that if I was to plot it right here, how the slope is steep. So basically the velocity would be pretty high at that point. But then as the line progresses, the line starts to slowly flatten itself out until it reaches this point where it becomes 0. So therefore, right here, it would be considered a positive. Yeah, still right here is still it's a negative deceleration because it's as it's going higher and higher, it's beginning to the slope is starting to become closer and closer to 0. And at this point, since it's going to go down, since the line is going to start going from left to right, then the slope is going to become negative until it reaches this point again, where it's going to flatten out and it's going to become 0. So it goes from having acceleration to at this point, somewhere around right here, it's the point of inflection, where the line starts to basically flatten out and it starts decreasing in acceleration and velocity until it reaches this point, and it becomes 0, goes back down, pointing down from left to right, and then it starts decreasing. But at somewhere around this point, another point of inflection exists right here, and then it starts to once again increase so that it can balance out to 0. And then it just shoots up to infinity. Basically, I'm just taking the same problem that I took before, where right here I finally found the second derivative, and then if I was to set it again to 0, if you set it to 0, that's just basically you trying to find where the points of inflection are. So it's 6t minus. Add it to both sides. So if I was to draw the line one more time, remember I established that at t equals 3, there's critical points. But at point 2, around right here, it starts to decelerate when it starts coming down, and then it comes back down to positive. Right?
Next slide.
Yeah, next slide. And here's just basically another problem I worked out. If you guys just want to take a moment and just analyze it to your own self, it's just everything I've been explaining. And I'm just gonna walk over here. Just give you a moment. Okay. Here I have a simulation where I have where I'm gonna just basically represent the same thing I've kind of been going over. So you see, as you begin to move, so you just see basically how from right here it went to the right and it started increasing in position, and then also the velocity just sort of slowly started to increase, and the acceleration was just kind of going wild. And then how at this point right here, he stops moving from actually right here. He isn't moving, so therefore there's no velocity or acceleration. And as he comes back to the main position, kind of speaks for itself. And if you have any more questions, just if you want to play around more with the simulation, just make sure you go to the to that website and Yeah, that's it. Thank you.